So I'm currently an architect engineer. I've been working in big data for the last 5 years. Last year I've been working mostly in deep learning prototypes and POCs. I've been working at digital labs for Wells Fargo for the last year, and then before that, many years before that, working Wells Fargo on many platforms and build-outs. I am in transition this month, so I'm actually speaking on my own behalf. So everything, all my opinions and suggestions are coming from me, not from Wells Fargo. And I'll be moving on to a new role in Melbourne, Australia with Think Big Analytics. So, not me. And so as I go through this talk, I'd love to hear questions or any other, if you have more information you want to get, you can come talk to me afterwards as well. So, okay. So deep learning. So a lot of deep learning things you've seen, is images processing, text processing, sound. It's awesome. It's like it does amazing things. The accuracy is better than humans on identifying categories. It's cat versus dog. How many use cases does that actually apply to in banking? So I look at these things and like, well, how do I use this in my day-to-day job where I want to use deep learning to apply it to in fintech or in consumer companies, and it doesn't really match. Like I don't need to do image categorization in a lot of cases. So what I wanted to talk about is how do you adapt your problems to what you can do with deep learning. So what's different? So consumer transaction data, what is that? That's basically, at a bank, that's basically what you'd see in your checking or your Visa statement. It's a list of transactions with dates. It has amounts, balances, some kind of description. But it also would be something like, any merchant would have this data as well, like what you buy, like Target has this data, it's consumer transaction data. It's very similar. So it's like some kind of description of what you've done, time information. And it also, usually have a lot of data, but not necessarily a lot of data per customer. So it's a little bit different. There's a lot of, so it's multivariate. So there's actually, for each time step, you have lots of values. And it's also not at regular intervals. So some things happen sort of, just something will happen one day and then 2 days later something else will happen. So it's a little bit difficult to work with in that way. And often when you're working with this data, it doesn't come out like here's a file for each customer. It comes out and here's a bunch of data for this month. It's all jumbled up and not sorted. And so if you have billions of rows of data, that's a bit of a problem to actually organize it by customer and to be actually train models. So what are some of the use cases for this? Short list, useful insights, predicting future transactions. There's all kinds of marketing use cases around that. Predict future spending income within specific categories. So see how much they're going to spend in utility bills and rent and mortgage. If you're looking at more from a product perspective from a company, like what kind of categories they buy, what times a year. And again, you can plug that into marketing. Categories of transactions, so actually qualifying what the transactions are for. Some cases you don't always have a description, but you don't necessarily know what that actual transaction is about. So looking at that kind of information as well. And then another use case on top of all that is you can detect, if you have a prediction in the future of what the transactions are going to be, and then the actual is very different from the future, then that's really an anomaly detection. So you could actually look for fraud. So if there's a different pattern that's happening than what you would actually predict from their model, you could use that as well. And not necessarily for fraud as well, but you could use like splurge alerts or something where if a customer is spending too much money, you can alert them like you're going over budget. So there's a lot of different use cases around that. And there's also segmentation. So for example, when you go traveling, you have a whole different pattern of what your transactions look like over time. So you could actually qualify, groups of transactions of different types of categories and segment them out. So the vacation time, there could be, this is happy hour. There's a whole variety of different ways you could look at that. And all that stuff's very useful to plug into different applications to actually drive not just business reporting, but actually drive how applications interact with you and like what messaging you get from your back-end systems. So how do we typically do this? So last few years, basically what we do, we say, we want to say, let's predict what your ATM, when you're going to visit an ATM and how much you're going to pull out. So we can basically say, hey, you're close to an ATM this time, you probably need cash. So why don't you go there now so we could send them a push message. So how would we do that? We'd build a model. We'd look at all their ATM transactions over time, build up a frequency model on that, and then build some kind of predictor that says, yes, this is probably the most likely time they're going to go to an ATM next, and then that basically is used to drive that logic. But then you have another use case where you want to look, okay, let's predict their balance over time. So you have to go and build another model for that. So it's like every little use case, you're building a separate model, you're doing the whole data engineering around that, and then at the tail end, what does that look like? It's a lot of work, right? So here are all the models you want to build. You're the data scientist, you're like overwhelmed, okay, now the next one's coming, the next one's coming. And they're really repetitive in a lot of ways, because it's the same data, the same sorts of transactions, but you're building it model by model by model. So there's got to be a better way, right? So why don't we do this? Let's apply deep learning. So given a history of disparate transaction types, predict the future transactions for an individual customer. So one thing this would do, so if you're building your own separate models per transaction type, you're kind of throwing a lot of information away. So there might be some correlation like, oh, they go to an ATM after they spent some money at a bar, or there's other things that you wouldn't necessarily pull into your predictive model. Whereas if you throw all that data into to building a model, it's going to build out some kind of representation of how your financial life is going to look. So it'll pick up on that. It also, as I said before, reduces the modeling design. So you're building kind of one model that predicts all the transactions at once as opposed to doing it one by one. And it's kind of a minor feature engineering. You're basically just feeding in raw data. I'm not trying to go pick out all the frequencies and to figure out what I need to do. And looking down the road, you could also basically use this. If you have something that's basically, you feed in transactions, like 20 transactions, and get out the next 10 transactions, then you could use that model as as a basis for other future models that you can build on top of that. So either through transfer learning or actually just having that feed into some kind of analysis where you look through the future predicted transactions. So any questions? So I'm kind of zipping through this. Okay. Sure.
So you're saying that the approach here, which is really different from classical statistics,
Yeah.
is there's not a single dependent variable.
No, it's just feed in the raw transactions and then figure out basically what you're trying to optimize is here's 20 transactions I know about, and then the historical transactions. And then when you're training the model, you're saying, well, here's the next 10. I know these two, right? You have a huge list of transactions. So what you're training is say, okay, optimize predicting the next 10, whatever they are, what do they look like. So now the difficulty there is actually transactions, it's not categorical, it's not like sentences, it's very different, right? So it's basically, it's dates, time, there's amounts, there's descriptions, and you want to predict all of that at once, right? So it's kind of hard. Yeah. So yeah, there is a little bit of feature engineering. As I said, it comes all jumbled. So it's really a matter of just sorting the data by customer. So that's the feature engineering. You're just saying, here are all the transactions. I need it by customer, and I'm going to train the model based on just on a customer at a time, right?
How do you define the classes if you have all the parameters? How do you create the classes, the output classes?
So we'll get into so that's a good segue. So let me get at how we structure. So I said before, we have the first step, 90% of your time structuring the data. So we have a billion transactions or whatever you have. So what you really want to end up with is, as opposed to just, this is a month of transactions for all customers, this is a month of transactions for all customers. What you really want is, for this, here's a group of customers for this month, and I want them all time ordered, like per customer, right? So what you do is you write a Spark job. It basically queries across some CSV file, whatever extract file you have, and then it writes into a data structure in HDFS. It basically sticks into, I call them customer groups. So you create a customer group for every, customers 1 through 1,000 will go here, and then you order them and put them into a single file in there. And what that basically does is when you sort them and put them in a single file like that with a group, when you're training your model, you actually don't want just one customer, you want like a batch size, like 1,000. So you kind of tune that so how you're structuring the data, you're storing it is going to basically feed into your training model, just for efficiency's sake. So you partition it by groups. that correlate to like a trading batch size. And then you write some kind of generator that will basically just randomly give you groups of customers. And it just infinitely will just say, oh, pick a customer, pick a range of transactions of that customer and give it to me one by one by one. And that's basically what you need to feed some kind of deep learning training model. And then one thing I learned really quickly is you want to start small. So as you're developing your whole framework for data processing and actually even for the deep learning part, you really don't want to start with a million customers. You want to start with 1,000, get everything to work with 1,000 customers, then ramp it up to 100,000. And then if your deep model doesn't actually converge with 100,000, then bump it up to 1 million. But just keep kind of slowly grow that data size. Don't try and process everything at once because it'll really slow you down. So, as I said before, how do you change this very disparate, like you don't do a regression, do you do categorization? It's all the stuff that's mixed together. So what if we treated the transactions actually as sentences, like in a word, so basically you as a consumer have a book that's written about you. It basically is composed of all the transactions that are ordered in time. So how do we convert your transactions to that? And because once you have that, you basically can use all these pre-existing, LSTMs and all the research around text processing, sentiment analysis for text, for generative models that predict text. You can reuse that stuff on your own data. So, transactions aren't Shakespeare, but we can make them sort of look like that. And one thing about transactions are actually, if you look, there's models that basically they feed in the corpus of Shakespeare, and then it will basically generate if you have a sentence, what would be the next sentence that Shakespeare would write. I think Shakespeare is very variable. That's probably a pretty hard problem, and actually the models work well. If you look at the transaction data, it's actually going to be it's much more structured, so you can make the sentences sort of look the same. There'll be a lot of repetitions, so the model should be able to pick up on that even faster and converge. And another benefit is most companies, if you have transaction data, you have lots of it. I mean, every year you're just generating more and more and more. So it's a really good training set there. How do we encode? So we're almost, this is basically the last step to finally get ready for training. So we have a list of time-ordered transactions. And so what we want to do is create a list of financial sentences that describe a customer's financial story. So going from sort of this, I don't like pointer's not working. Basically, you just go from 601 502 credit check. That's like a description. There's like a little account number that's masked out. It has an account, and then there's a balance, right? So very basic. What you really wanted that to do is you want to categorize the date. So you're saying, on the Friday, the 1st of June. So you're getting some of that periodicity information into the sentence. A deposit of amount of $500. And how do you categorize the amounts? Is you don't actually use the exact amount. You say between 0 and 10, or 10 to 20, 20 to 30. So you basically build categories or words that represent all the different amounts, that you could have. And that would basically work for balances or for the actual transaction amount. So what you're doing is you're basically building these sentences up in order, right? Now once you have all these sentences, you can create a dictionary, an entire corpus of all the words in all your financial transactions across all customers. What are the different transaction description words? What are the different amount words? What are the different date and time? You could actually put like holiday information, the day after 4th of July. Really, if you have enough years of data, the model should probably start picking up on that anyways. You wouldn't necessarily have to put the holiday information, but the more upfront you can get information, you can give it, the better it'll do, quicker. So once you create a dictionary, you have a list of basically, all these words that have an ID associated with them. $100 to $200 is ID 500. Credits 545. This is just randomly generated, right? And then you pick out. You say your dictionary size is going to be 10,000 words, which should cover most transactions, I would think, for a single company. And then you can encode that. So you go from this structured, uncategorized stuff to actually just a list of IDs. And some of those IDs actually represent like the end of a transaction, or you could actually have some padding in there, so you could actually pad as well. So what does this look like? This looks like a text. You have a question? Yeah.
Are you suggesting from the writing out those sentences that's actually a human effort?
No. No, that's just kind of showing what's going on, but you're not, I don't really have a phase where I actually generate these sentences. It's just, all I'm saying is like from, the date information, it basically creates like three words for the date. One would be like Friday, one would be, first of the month, and then the other one would be the month.
Just trying a conceptual analogy.
Yeah, just conceptual analogy. Yeah, exactly. Yeah. Sure.
Is the schema structured, or is it sort of open key value pairs?
For the dictionary, it's just key value pairs, right? It's just ID represents word, right? The structure, the sentences are highly structured, so you'd have it in the same order, and you probably have it like the more structure and the same. If you can do it the same each time, then the deep learning network will pick up on that quicker. I mean, theoretically, you could probably just throw it in randomly, and it would try and do sorting, but it would just take longer to converge. So. Any question?
So, are the descriptions, the entire descriptions a word, or you actually parse out the words?
The words, yeah, individual words. Yeah, so every, yeah.
And you combine the monetary amounts and those categories within?
So yeah, so the monetary amounts are actually, I basically create a category. So, from, word IDs from 0 to 10,000 are all represent numbers. And you have to figure out how you want to do that based on what your range of amounts are. So, simply you could just do, 0 to 10 is, ID 1, 10 to 20 is ID 2, so on, right? So when it comes out, I mean, the sentence is going to be a little bit different, right? It's not saying balance 201, it's going to say balance around $200, right? So.
And each transaction is a sentence? Or
Yeah, a sentence. Every transaction is a sentence, and then you feed individual customers in order, right? So you want to look at a customer at a time as you're training. You say, okay, I'm going to feed in this customer, this range of transactions, and then get this range of transactions from an individual customer. But then you do different customers repeatedly. Right?
So each customer is a document of sentences?
Yes.
Okay.
Every customer is basically a book, right? And then all the books are all the customers. Yeah. So we trained the models. We got the structured data engineer brought it in. We have the word embeddings. Well, actually, we don't have word embeddings yet. What we're going to do is create word embeddings. Does everybody know what word embeddings are? Basically, you have an ID, and you turn an ID into a vector. So if you have we have a dictionary right now of 0 to 10,000 words. What we'll end up with is every word will have, what we want the model to do is create a vector for those words, so words that are associated with each other will be very close to each other in vector space. Okay. And it's very common, if you like word to vec, it's a very common thing to be done. And then let's look at let's just pick out what's the latest deep learning model that works really well on text processing. There's a new one probably every month. Pick the easiest one to deal with, to start with, and let's just plug that in and see how it works. We have, so the two I'll talk about today, there's probably many more, basically using some variant of RNN, which would be like an LSTM, and then also there's a GRU as well you could possibly use. And then also let's look at maybe trying using a CNN. It's a little bit different how we have to structure the data, and there's trade-offs in flexibility and training time, but we'll talk about that. And then, yeah, as I said, you can basically just use the next best learning model, deep learning model you've found. So you can apply to almost anything. So I'm not going to get into like the architecture of the actual deep learning model, because I said you can sort of pick what you want and try that out. But the basic idea for CNN, so it's a stateless model, right? So you have to feed in a whole list of transactions out. So you feed in 20 transactions, and I want to get 10 out all at once, okay? So basically you feed in word IDs. There's an embedding layer that basically will train the transformation from IDs into vectors. And then you have a bunch of convolution blocks, like 1D convolution blocks. So it's not an image, so it's basically a list. So you have 1D convolution blocks. And then you have a fully connected model. And that fully connected model will basically give you a bunch of one-hot encoded vectors that represent the words that are being output. So 20 transactions, all the words for 20 transactions feed in, and then 10 will come out. So now there's some drawbacks to this, and we'll talk about after we go through this. Now RNN. So this is basically a recurrent neural network, and these are stateful. So With a stateful, it's different. You're not, as opposed to feeding everything at once, you're feeding it word by word. So you basically feed, in the order of the book for the customer, you feed it word by word, the word IDs. Same thing, it goes into an embedding layer, and then you have a bunch of LSTM blocks or GRU blocks or whatever network you want to use. Goes to a fully connected, and then you have one hot coming out. And that one hot is basically just representing one word at a time. So one word in, what's the next word? One word in, what's the next word? And that's basically what you're training on it. Now, what the difference here is, so you have all these one word in, but what you do is you feed in, so let's say you have 100 days of transaction. You feed words in for 100 days, and then say, well, I don't know what's next. And the model will say, well, this is the next word. Well, what's the next word after that word? You feed that word back in, and so it'll basically generate the transactions as far out as you want to. Right? Same thing they do for generative models for text. So you can see there's some trade-offs. So LSTMs, what I've generally found, they converge a lot slower. There's a lot more matrices that have to happen. There's a lot of processes that aren't as parallelizable. But there are some new RNN type networks out there that are improving on that, so that's promising. CNN basically requires a large amount of fixed transactions feeding in at once, and then you get a fixed amount coming out. So it's not as flexible. So you have to say the same amount in, the same amount out every time. Whereas the LSTM, you can say, I only have 20 transactions, so give me the next 3. Or you can be it's more flexible in that way. Again, I said data prep for large data sets is time consuming. I just want to keep mentioning this. It's like start small, because just to get your network architecture to work, like you only want to have a small data set and just iterate quickly on that. So don't start out with 1 million. And then some possible things you might want to try as well if things aren't working is you could try and, there's a lot of, go ahead. Sorry. So the CNN model would basically, you'd have a bunch of, I call it transactions or sentences, right? That's the corollary. So basically you feed in a bunch of sentences and then it's predicting the next 10, right? So it's a fixed amount out. The LSTM is you're just doing it word by word. So I feed in a bunch of words and it's keeping state on what you fed into it previously, right? And then it's going to come out on the other end, like this is the next one, this is the next one. So you can basically use that, you just run it forward a couple more times by feeding in what it predicted back around, and it'll just keep it generating transactions out. So they're a little bit different how the structure is. Yeah. So usually the batch is a group, as I said, it's a group of customers is the batch size, but the LSTM, you're basically resetting the state after each customer. So you're not saying, after customer A, I start on customer B. I don't want it to keep the state for that customer, so it's kind of resetting that, right? And if you use like Keras, it's like a one-line command, like, okay, new customer, reset state, and it'll continue on. So. Okay. So yeah, as I said, some workarounds. So there's going to be a lot of noise because if you think about transactions, there's a lot of kind of low-level stuff that's going on. Like you might, buy gum in a store. It's like very random. So you can sort of aggregate all that stuff. But then you're starting to do more feature engineering. But you could basically on the output say, well, I'm going to feed all the raw inputs in, but on the output, I'm going to have a sentence that says, I don't want to hear like all these random noise sentences. Just tell me, I'm going to add everything up and say, just predict like anything under $10 is just like random petty expenses or something like that. So that's another way that might improve the convergence a little bit. So what do you expect to work? So the embedding layer, as I said, you're going to get, if you feed enough data in and you start to see convergence, what you're going to have is these word vectors. It's not necessarily in 3D space, but it's going to be like 50 space vector. But if you compress something down and looked at it, you'd see things like payments that happen on certain days would be close to each vector in space. You'd see, if you buy coffee on Monday, then coffee might be close to Monday. These are just examples. It's not real data. So, but that's basically what the word embedding does, and that helps the model as well because it knows words are associated to other. It'll associate the, as it's predicting what's coming next. Transactions that have a well-defined frequency should be picked out, and that basically, if you give it enough data coming in, then the output data should actually pick up on those large transaction amounts that are repetitive, like monthly payments and things like that. Transactions without a well-defined frequency produce sort of scrambled descriptions. So if you for some reason you have 2 phone bills or something and you're paying 2 things, and maybe you'll get like one output that says AT&T plus Verizon is this amount. So you get kind of strange. But again, if you feed more and more and more data, over time it actually should figure out those patterns and be better and better at it. So. And you would expect the amounts to be very close to the actuals. It's not going to be exact, but you should get the amounts that are coming out for the transaction to be close. But also you can expect some strange things. So you get these weird, as I said, you get these weird combinations or descriptions where it doesn't know quite what's happening, but it's doing some probabilistic merge of what the actual words, the sentence is going to be. So you'll say, the previous example I said, it'll say, well, you're not just AT&T, it'll mix up 2 bills, a description of it, and maybe the amounts will be averaged out. So but again, if you feed more data, it should slowly be able to separate those things out better. One thing I think some problems with this model is it kind of gives equal importance to every word. So it's basically looking at, the loss function is basically looking at, okay, how many words did I get right in the sentence? Whereas some words are actually much more important than others, like the amounts may be more important to you. So you could sort of explore looking at a better cost function that costs, the certain words that are incorrect would have more cost as far as when you're trying to optimize. Again, more data, better convergence. And then within categories, the amounts sort of will line up pretty well. So, and some descriptions will be jumbled. Any questions? So I'm sorry, I didn't see a whole other section over here. Yeah. So I can't get into the specifics of that, as again, I'm not representing Wells Fargo. It gets pretty good. So again, the more data you feed in, the better the accuracy we'll get. So, yeah. Sure.
About any applications, and you said in the beginning that you can solve lots of problems and use this as an upstream to various downstreams. Do you have any applied examples of this?
So I think one I was excited about was the fraud detection. So basically, if you feed in, I have all these transactions and I split them like 20 and 10, and I already have the 10 as well. I say, okay, here's the 20. What's the model predict? Now, how close is that to what's the loss on that? And if it's like through the roof, then there's this anomaly there, and that basically can flag a fraud interaction, or it could flag a budget. Say if you're going over budget, it'll say, oh, you can actually send a push notification to the customer and say, hey, you're overspending according to your budget amount. So. Well, there's a whole bunch of application logic behind that, so that's really up to how you want to build something. So, yeah. But the fraud is easier. It's like, okay, we established we don't want to pay for this X amount of fraud, and if it goes above this amount, we know that's going to cost us this much. So then you can shut down a card, you could push notify somebody. So. Yeah, I think the fraud one is easy. It's a little bit easier, right? If you're showing the raw data of the transaction, they'd see the shark course. They'd be like, what is this? It doesn't make any sense to me. But for the fraud, where you're just trying to predict how far off it is, that works really well because it's more just taking an average of how bad or good it is.
Is it problematic that sometimes customers' largest transactions are kind of one-offs?
If you think about it, it's probably not necessarily. Like if they have one, it's probably going to happen later on, like a mortgage payment or property taxes. It's kind of twice a year, right? And I think if you think about it, it's going to be training over multiple customers. So maybe there's one customer that just started. He just became a customer a month ago, right? So you don't have much data on him, but you have customer on millions of other other data on millions of other customers. So if we just have one input, like they just paid their bill once, we know it's this type, and we have a million other customers that paid it, it would actually predict that pretty well, right? So that those situations work. One-off transaction, if they just sent randomly sent $10,000 to somebody or whatever, it's not gonna. It would actually probably try and figure out. It would probably think that's like a mortgage payment and assign it, a year later or something like that. So.
Was there any distinctions about credit card, debit card, the checking account transactions that would be more or less effective?
That's what's interesting because I think what you could do is you could basically just throw it all in together, right? Depends on what you want to do, but if you threw it all together, it's very similar structure if you structure it in this way. So the dictionary, maybe the credit card descriptions and the DDA description, the credit and the checking descriptions might be a little bit different, the words they use, but sometimes I use a credit card, sometimes I use an ATM card, and you kind of use them interchangeably. So if you can just combine that data, it'd probably be better in some ways. So. You can interleave it. And you could even throw in other types of transaction data pretty easily. Huh?
What has it been applied to right now? Is there a particular type that it's been applied to so far?
So we worked on DDA. I worked on DDA's checking and on credit card data. Yeah. Right.
So I'm still not totally tracking on this. So let's take the fraud detection example.
Okay.
You have all of these transactions.
Right.
Somewhere along the line, there needs to be a indicator. Oh, there was fraud on this account. Either that is entered as a transaction. I mean, how do you, if you're trying to detect fraud,
Actually, for this one, you don't need that label because basically all you're saying is So let's say if you can somehow make a picture of what fraud looks like, right? So or you had to make a picture of what your daily transactional life looks like, right? If the picture changes all of a sudden, like before you had something looks like this, and now all of a sudden it's like this, I don't need a label. All I need to do is like sort of take a statistical difference between those two things and say there's a huge change here, something's going on, right? So I don't actually need to know there's a fraud event.
All you're doing, I'm not trying to minimize it, is looking for, you're establishing a pattern, you're projecting some future pattern, there's a certain residual error with that, and now something new has appeared, and wow, the residual errors have become much larger, something's happening.
Right.
Is that the spirit of what we're doing?
Yeah, that's for anomaly detection. That's basically what you do. That's what's kind of nice about anomaly detection. You don't necessarily need the labels. You need to establish sort of like the threshold and you can use, if you do have labeled like, oh, these are the fraud transactions, you probably want to establish that threshold to minimize the cost because there's a cost associated with shutting something down. There's a cost associated with not doing it. So you have to tune that based on the data. Go ahead.
Because of the sort of sharp horse problem, if you try to do something customer facing, I mean, the risk of getting into sort of something spooky, which is like, hey, how did you know? It's outside my pattern, how closely you're watching my patterns.
Yeah. I think that's.
Fraud is a benefit, but
Yeah, for fraud, that's why I say fraud, people are like, fine, I'm glad they figure something else. And there's definitely a lot of bad use cases out there where they send out marketing material saying someone's pregnant and then they're dead. That's not a good use case. You have to be really careful, but I think that's really sort of the product development, application development's responsibility to try and figure that out. The model is just kind of just generating what we think is going to happen in the future. So how you apply that and how you use it, you have to be careful. Right? And I think for me, it's like if it's doing fraud or it's giving me some kind of benefit, then I'm okay with it. They have the data anyways. They're doing something with it. So I think you have to provide a value in order to justify using it.
So just to that example, someone who doesn't have a lot of variability in the patterns, maybe pick up fraud, somebody with a great deal of variability, it's going to be much tougher.
Right. That's true.
You try to feed into other types of data, for example, social or digital, into that.
That's what I think is cool about this, because basically you could interleave things like that. Like if you have other text-based data, you possibly could interleave like customer service data, and it would, again, it's really a matter of how much. The more stuff you throw at it, the more complex the model's got to be, and the longer it's going to take to train it, and the more data prep. So, but you could do things like location data would be interesting, because then you can. I'm sure there's a lot of stuff that's really important about location. More sort of just demographic data, per customer demographic data would also be interesting to see, because if you're in a certain demographic, you maybe have people that are similar to you, and it would be able to figure out, oh, this demographic does this, and then we can predict a little bit better. So you definitely can interleave a lot more stuff into there.
Can I make a comment on that point?
Sure. Yeah.
So one of the research we did in our group at MIT, we did find people are very habitual even if there is very high variability. And the time when habits change, actually there's a significant correlation with life event changes. So when someone goes from employed to unemployed, suddenly you would see their exploitation versus exploration behavior completely changes.
Mm-hmm.
And then purchasing behavior accordingly changes, becoming the locations they're habituated to.
Right. So as far as location and, yeah, it's interesting. Yeah, I think that's one thing I'm interesting too, is like you can figuring out life events. So this is a thing called like semantic segmentation, where you can take an image and it'll say this shape of this is this, and this is this, and it basically go to an image and figure out all the different categories and pick stuff out. So you can think of the same thing, sort of if you have this whole book on a customer, you could have semantic segmentation and say this is they're on vacation, this is they're at happy hour, this is, you kind of qualify like a whole set of transactions or periodic transactions.
How does the algorithm deal with missing data? For example, a particular brand of credit card could be
Mhm.
Apple wallets.
Mhm.
Sometimes it could be the habits could be shifted to other venues that's not detected.
Right.
So how does the algorithm react to those things?
Yeah, I mean, if you don't have the inputs to predict off of, it's probably not going to work that well. So if you're missing, if they have another bank or they're using something else, and we don't have those transactions, and it would be hard, and they go back and forth, it might be kind of hard to predict. But I think if you have one transaction with a description, you probably can predict pretty well what the next one's going to be. So if we just have one, it can predict the next one. But we can't predict the ones we don't know anything about, of course. So, yeah. Okay. So again, some of the uses. So we've built out, just by doing this, maybe I could throw away the whole prediction, what it's predicting. But at least what I have this word embedding, so I can use the word embeddings over again. So I have an ID that goes to a vector, and I can reuse that for other models. We could also do transfer learning. So we also have there's all this structure that's been built into this model it's just learned representations and how to model customer behavior. We could basically use transfer learning and chop off the bottom layers that are doing the categorization, and then create our own categorization or sentiment or whatever you want to do. And then you just need a lot less data than you did initially, because you already built a lot of that structure and the modeling of the customer in there. Again, more data, more models. So not just more data that you have, but interleaving other types of data like social data, as you mentioned, interleaving different types of accounts. So the more stuff you can put in there, I think the more interesting results you get. Again, whenever a new model architecture, I think there's going to be more improvement in the RNN models. So where they're going to be able to parallelize a little bit better and train faster. So looking at doing the same thing with those types of architectures. And then deployment, I think deployment is actually a big area that's of interest to me, because you can create a super accurate model that's like 99%, but if it executes in 1 second, then it's not very useful over a million customer base. And especially if you're doing fraud and you want to do something in real time, then you need something that executes quickly. So the trade-offs between how complex your model is and how accurate you really need it to be in order to get done what you need to get done is important consideration. Yeah. So any questions? Great.
When you think about updating the models, in the sense that if you use a customer database, you have the customer that's 5 years old, things change, behaviors change. That probably is a bad model for the customer today.
Well, it's not a model it's a model over the whole customer base. So as the population changes, you'd want to retrain on a periodic basis as you get more data. But it's not geared towards one customer. It's basically feeding in all these customers and all their different transactions and modeling that. So if somebody else already had a child, had a kid, and then their behavior changed, you'd probably pick up on that other customer that just happened to, because you already had their data set kind of go through and train the model. And it really you have to look at it over time and see how it's performing, right? So I think for this stuff, it's probably, if you have a great recession, then maybe you have to retrain quite a bit, right? But typically things aren't changing that rapidly over a huge population. Maybe what if you added a new, like you added a new region to your data, then yeah, you probably want to retrain, right? Things like that.
What kind of lift do you observe?
I can't talk about that. Yeah. I mean, really, just how would you? The idea is not to apply it to the exact same problem, but just kind of rethink your problem so you can use the deep learning. That's the main topic I want to get across. Sorry.
Question is, I don't know why the CNN is good for this application. CNN normally used for the computer, for the imager.
Right.
Imager that is actually something, because imager, the neighborhood of the pixel is highly correlated.
Right.
And CNN make a lot of sense. But this, for the each transaction, the neighborhood doesn't make any sense.
Well, if you look, so it's not a 2D CNN, right? So it's a 1D CNN, right? So it's looking at, and you're having stacks of them, right? So it's building up. It's not looking at just one region, but it'll eventually get to associating regions that are far apart from each other. Yeah. There is a fully connected at the bottom, but it's stacks of CNNs. It's not just one layer. And you're right. It takes I think there's some things where it seems like the edge transactions don't get picked up on as well, but if you move around, then you should eventually get that. I think I'm all. We up with time? We good? Okay, last question. Sorry.
For the CNN, was there specific windows that were affected?
It actually worked fairly well. It wasn't. There was, as I said, there's the ones that are the random noise stuff. It was hard to find. The big transactions worked pretty well.
And transactions, under transactions?
Oh, we didn't go that wide. Because if you go too wide, it gets much harder. Because if you look at that's one of the problems with the CNN is you have to feed in all the transactions at once, so the network complexity explodes because basically you one-hot encoding all those words at some point, right? So there's huge network sizes. And so you only want to do like 20 or 30, and then the LSTM works better in that aspect when you want to do more. So. Great. Well, thank you. Great questions.